Hello and welcome back to Zig's Math Lessons. Today it's stretches of functions. The graph of y equals a f of x is a vertical stretch of the graph of y equals f of x. Note, vertical means up and down, so it's an up and down stretch. Because the output y values, which is its elevation values, are multiplied by a. Note, if the absolute value of a was less than 1, then this turns out to be a vertical compression. Because when we multiply the output values by a, we're multiplying by a number less than 1, like 0.5, and the result is actually a vertical compression. But in general, this is a vertical stretch by a factor of a. Here's a graph of a function y equals f of x, the blue line. We can tell it's a function because it passes the vertical line test, and it's a set of ordered pairs such that for every x there's only one y value. And let's use this to sketch the graph of y equals 0.5 f of x. Now this means the y values will be multiplied by 0.5. So we go to the corner points and we consider the y value here, which is minus 2, and multiply it by 0.5, or take half of it, and that becomes minus 1. And we do this with each corner point. Consider this point, the y value is 2, multiplied by 0.5, and that becomes 1. Same with this one, the y value is 2, multiplied by 0.5, it becomes 1. The y value here is 0, and multiply that by 0.5, and it remains 0. Join the points together, label your graph, y equals 0.5 of f of x. Now we're going to graph the function y equals 3 root x. Solution? We see this as y equals 3 f of x, where f of x is root x. So this is our parent function, and we're going to call that our f of x, and we're going to take 3 times that, a vertical stretch. The graph of y equals root x will be vertically stretched by a factor of 3 because the y values will be multiplied by 3. So first let's go to the parent function and find out where those points are. Well, we know that there's going to be 1 at the origin, and then when we displace ourselves 1, we go up the square root of 1 because we're looking at the parent function being the square root of x. And when we go over 4, we'll go up the square root of 4, which is 2. And when we go over 9, we'll go up the square root of 9, which is 3. These are points from the parent function, the top half of a parabola that opens to the right. Now we'll take the y values at these points, and we'll multiply them by a factor of 3. So the y value there is 0, so 0 times 3 is still 0, so that one stays put. The y value here is 1, multiply it by 3. Now it becomes the number 3. The y value here is 2, so we'll multiply that by 3. So the y value is 2, multiply that by 3, and we get, well, 2 times 3, 6. Note, we don't go up 6 more, we go up to the number 6. It's actually 4 more. And let's consider the other one. When the y value is 3, well, the new y value will be 3 times 3, which is all the way up here at a y value of 9. Join these new points together and label your graph. Y equals 3 times the root of x. Let's consider horizontal motion. The graph of y equals f of bx is a horizontal compression of the graph of y equals f of x. So if the factor was out front, we would multiply the y values by whatever that factor was. When the factor was out front, we called it a. Now we're putting a factor into the input station and calling it b, and it has to do with horizontal motion. And in this case, the input values are going to be divided by b. Note, if the absolute value of b is less than 1, then this turns out to be a stretch, because when you divide by a number less than 1, like when you divide by 0.5 or when you divide by a half, you have to invert that half and multiply it. So usually, generally, when there's a factor at the input station, it's a horizontal compression because the x values are divided by whatever that factor is. Let's do an example. Here's an example of a given function. You're given some function of x. It might be one of the parent functions, but for now, it's just some random function. And we're going to graph the transformed function, y equals f of 2x. Now we see here at the input station, there's a factor on the x. That means divide the x values by 2. So let's start with this point. We see the x value is minus 6. Divide it by 2, we get minus 3. Notice the y value stayed the same. Take this point, we notice the x value is minus 2, so we'll divide by 2, because we're dividing by b. Negative 2 divided by 2 is negative 1, but the y value stayed constant. Next corner point, the x value is 4, and we'll divide it by 2. So 4 divided by 2 is 2. Y value stayed the same. And the x value here is 6 divided by 2. So it becomes the number 3. Play connect the dots and label your graph. Notice the new graph is a horizontal compression. Now let's state the equation of some curves. Let's start with this. You're asked to state the equation of a curve. Okay, recognize the parent first. It's a parabola that opens up. And we notice that this particular parabola has been shifted down 4 units. The vertex would normally be at the origin, but it's been shifted down, so we'll have to do our up-down shift from the previous lesson. So outside there on the end, we'll put x squared minus 4. That shifts it down 4. And so the next problem to be solved is how do we deal with the fact that this parabola has been vertically compressed? It's been squished down. That's why it looks so fat. Well, let's just put a number there, a, because we know it's some vertical stretch or compress. So we'll call it a. And the question is, how do you find a? A is always actual over expected. Now let me explain this. Since this is a parabola, and I'm pretending that this is the origin, if I displace 2 to the right, I would expect that I would go up 2 squared, which is 4. So I would expect to go up 1, 2, 3, 4. But I don't go up 4. I only go up 1. So actually went up 1 when I expected to go up 4. So actual is 1 and expected was 4 for this point. So actual over expected is 1 over 4, and that's A. A is always actual over expected. Now we know what A is, we could state the equation. See this point? Let's test it by subbing it in here. If I subbed in the x value 2, I would expect to get the minus 3 value for y. Let's try this. Sub in 2. Well, 2 squared is 4, and 4 over 4 is 1, and 1 minus 4 is negative 3. So this point works at least. Sometimes it's good to test a point. Let's do it again. State the equation of the graph. Well, we see that it's a half a parabola that opens to the right. This is the beginning point, the parent function. It's a half a parabola that opens to the right. Oh, it's been transformed, it's been shifted and stretched, sure, but it's a half a parabola that opens to the right, so that's our parent function. That's why we learned the parent function. Great. Now this one has been shifted to the right too, because normally that vertex would be at the origin. So it's been shifted to the right too. So at the input station, from our previous lesson. We have to take this parent and shift it to the right 2, like this. At the input station, it's x minus 2. Notice this would be wrong because this minus 2 isn't in the input station. It's outside. It's outside this root sign. So working with this now, which is our half a parabola shifted to the right 2, we need to figure out the a value for a good vertical stretch because this has been stretched vertically. So let's consider a has to be actual over expected. Well, if I went to the vertex point and I displaced 1 to the right, I would expect, since it's a root function, I would expect to go up root 1. I would expect to go up 1, because that's the square root of 1. But I don't go up 1, I go up 2. So I actually went up 2 when I expected to go up 1. So actual over expected is 2 over 1, because I actually went up 2 when I expected to go up 1. So the a value is 2, and we can write our equation. Test a point, like 3, 2 to confirm. Let's test this point 3, 2, see if it fits. So I'm going to take 3, an x value of 3, input it here. 3 minus 2 is 1, root 1 is 1, 2 times 1 is 2. So if I input 3, I do get, in fact, 2, which is what I'm supposed to get, because the point is 3, 2. In grade 10, you learn to graph parabolas. This is grade 11, and we're still graphing parabolas, but we're getting more sophisticated, we're getting more accurate, we're getting better at it. Let's graph this parabola. We see that it opens down. We see that it has a vertex at 5, 9, because we change this sign, leave this sign. So we go to 5, 9, and we put a point there. This is the point 5, 9, from which we'll draw a parabola that opens down, but we're not going to be casual about this. Let's see if we can be accurate. When I go over 1, I would expect to go down 1 squared, which is 1. Pretending here that this is the vertex, and I'm doing the parabola that opens down, go over 1 down 1 squared, which is 1. But wait, you have to multiply that by a quarter. So go over 1 down 1 squared times a quarter, which is 1 times a quarter. And because of the axis of symmetry, a point appears there as well. Let's go back to the vertex and displace over 2. Why? Because we need more points. So if we displace 2 from the vertex, we would go down 2 squared, which is 4. 1, 2, 3, 4. But wait, we still have to multiply the output value by a quarter. So 4 times a quarter is 1. So when you go over 2, you go down 2 squared, which is 4 quarters, which is actually 1. So when you go over 2, you go down 1, and our axis of symmetry puts a point there. It's symmetric about the origin, remember? Back to the origin, let's displace over 3, down 3 squared, which is 9, 9 quarters, that's 9 divided by 4, that's 2 and a quarter. So over 3, down 1, 2 and a quarter. Right there. Axis of symmetry puts a point here. Back to the vertex, over 4, 1, 2, 3, 4, down 4 squared, which is 16 quarters. 16 times a quarter is 4, so down 1, 2, 3, a point appears there, and by the axis of symmetry it appears over there as well, because we're making a symmetric picture. Back to the vertex, over 5, 1, 2, 3, 4, 5, down 5 squared, which is 25 quarters. Well, that's like 24 quarters, which is 6 and a quarter. So 1, 2, 3, 4, 5, 6, and that extra quarter, because it's actually 25 quarters. Axis of symmetry puts a point there, and let's do 2 more. Go to the point 5. Over 6. 1, 2, 3, 4, 5, 6. Down 6 squared times a quarter. So 6 squared is 36 divided by 4. 36 divided by 4. Good thing you know your times tables and you know that 9 times 4 is 36. So 6 squared is 36 divided by 4 is 9. So 1, 2, 3, 4, 5, 6, 7, 8. Look at this. We have the x-intercept, and an axis of symmetry puts one there as well. Back to the vertex over 7. 1, 2, 3, 4, 5, 6, 7. And down 7 squared, which is 49 quarters, which is going to be 12 and a quarter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a quarter, right to there. And by symmetry, join them together, label your curve. I'm not really Ziegelviat, but thanks for watching. If you liked it, leave a like. If you like the content, then please subscribe. And I'd suggest that you ask a question if you have one in the comment section.